Welcome to this third lecture about cellular automata. In this lecture, I will show you how you can create your own cellular automaton. I will here use the software R for the implementation. The reason why I use R is that it is free and includes simple functions for mathematical operations and visualization. One drawback with R is that it is pretty slow in comparison to, for example, C when using loops. However, at the end of this video, we will see how we can avoid such loops in R. Note that this lecture is intended for beginners and not for experienced programmers. The code is made as simple as possible with no fancy stuff. You can find the following code on my homepage. If you do not have R installed on your computer, you can download it freely from the following website. Note, if I run the code in RStudio on my computer, the images do not update fast enough during the computations. I therefore recommend that you use R and not RStudio. We'll here implement the game of life model in R. At the end of this lecture, you should be able to generate the same simulations as the ones shown here. So, open a new script in R. The code that will be shown in this video should be entered in this script. We begin by assigning the value 20 to the object that we call n, which will store the size of our grid. Next, we create a matrix with 20 rows and 20 columns, including only zeros. This square matrix will represent the lattice, or the world of our cellular automaton. Note that the text to the right-hand side of the hash symbols will only be interpreted as comments by R. After the hash, you can write anything you like. The object that is called mat will store a matrix with 20 rows and 20 columns. Currently, the matrix holds only zeros, which represent dead cells in the game of life model. Note that the array indexes start at 1 in R in comparison to, for example, C or Python. Next, we add 10 live cells by adding the number 1 to rows 5 to 14 in column number 10 in our matrix. If we print the matrix, we will be able to see the ones in column number 10. Since we use synchronous updating, we need a temporary matrix. We create such a matrix by simply copying our previous matrix. The temporary matrix has the name temp_mat and includes the same ones and zeros as the mat matrix. Next, we plot our matrix where the numbers should represent a specific color. We can do this by using the function image in R. I here selected gray color for zeros and sea green color for ones. The first argument should include the matrix containing the values that should be plotted. However, the image function will plot a 90-degree rotation of our matrix. To simplify the interpretation of the image, we need to transpose and reverse the order of the matrix before we plot it so that the layout of our original matrix reflects the image. If we would instead have used the original matrix as the first input, the image would show a counterclockwise rotation of our matrix, which can be a bit confusing to work with. Next, we use the function grid to put a grid on the image in order to see the cells in our lattice. We want simple solid lines for the grid, so we set the line type to 1 and use the color gray 70 for the lines. Also, we want the same number of cells in the grid as we have in our matrix. We therefore set the arguments nx and ny to n, which we previously have set to 20. The grid will therefore correspond to the size of our matrix, which is exactly what we want. In this example, we like to update the matrix 200 times. To do that, we use a for loop where k is first set to the value 1 and then increased by 1 after every iteration. When k equals 200, the iteration will stop. Only the code that is between the left and right curly brackets will be repeated when we run the code. Next, we create 2 additional for loops that will be used to update each cell in our lattice. The variable or index I will be used for the rows, whereas the variable j will be used for the columns. For example, if I is equal to 10 and j is equal to 5, this means that we are currently looking in the element on the 10th row in the 5th column. For simplicity, we'll check all elements of the matrix to see if the state should be updated or not. Initially, both I and j are set to 1. j is then increased by 1, which means that we now look in the cell at the first row in the second column. And when j is increased again, we now look in the third column, and so forth. Once j has reached the total number of columns, the iteration stops. The above for loop then increases I from 1 to 2, whereas the second for loop starts over from 1 again. We therefore now look in the second row in the first column. Then we move to the second column, and then to the third column, and so forth. When both I and j have reached the value 20, we have checked all elements of the matrix. For every cell that we check in the matrix, we'll update its state according to the rules in the game of life model. The code to update the states should therefore be placed between the two left and the two right curly brackets. However, before we start to check the neighbors for each cell, we need to determine what we should do at the edges of the matrix. In this example, we will use periodic boundaries. This means, for example, that if we check a cell that is at the right edge of the matrix, then its neighbor to the east is the cell at the left edge of the matrix at the corresponding row. To implement periodic boundaries, we first set the position of the neighboring cells to east, west, north, and south. For example, if we are currently looking in the cell at the 10th row in the last column, then I is equal to 10 and j is equal to 20. Since e is equal to j plus 1, e will be set to 21. Since the neighbor to the east is outside the matrix, its neighbor will be found on the opposite side of the matrix. We implement this by using an if statement. If e is equal to n plus 1, which is 21 in our example, then the object e will be reassigned to the value 1. Similarly, if the current cell is in the first row in column number 9, then its north neighbor is the cell at row number 20 in the corresponding column. Next, we simply sum the values that are in the more neighborhood. Since live cells are coded as 1s and dead cells as 0s, adding these values will result in the number of live neighbors. Next, we simply implement the rules for the game of life model. For example, if the cell is a live cell, which means that its state is equal to 1, and the number of live neighbors is less than 2, then we only fulfill the first condition. The cell will therefore die according to the first rule of the game of life model. We therefore set the corresponding cell in the temporary matrix to 0. The same is also true if a live cell has more than 3 live neighbors. If the cell is alive and it has 2 live neighbors or 3 live neighbors, we do not change its state. The temporary matrix will therefore be set to the same value as the current matrix. Finally, if the cell is a dead cell and it has exactly 3 live neighbors, the cell becomes alive and we therefore change the state of the corresponding element in the temporary matrix from 0 to 1. Once we have updated all cells in the temporary matrix, we update the current matrix by overwriting its content with the content stored in the temporary matrix. We then plot the updated matrix using the same code as before. The only difference is that we now set the argument add to true, so that we add the new image of the old one. In order to see how the pattern changes in the image, we need to pause the loop. The time interval is here set to 0.5, which means that we will see the image for about 0.5 seconds. Okay, so if you open R, you can open a new script here, and then you write your code in the script like this. And to run the code, you can select the code, and on Windows you can right click and press this option here, or you can also use Ctrl+R on your keyboard. If you use a Mac, you press Command and Enter after you have selected the code. So if you run the code, you should be able to see the simulation during time here. And to break this loop, you can go to the console and press Escape. To simulate the glider, we change the initial pattern to this. This initial pattern will generate a glider where the pattern is moving. So if we change the initial pattern to this one, so that we get a glider that looks like this, then if we run, the pattern will move. So it's going pretty slow now, but if we reduce this value here, we'll see the image a shorter time. And how small this can be depends on your computer, for how fast it can update the image. So if we break here, we can also create a bigger matrix. For example, 40 rows and 4 columns. And you can also change the color. Maybe you would like to have a red color for the dead cells. Go down here. In our previous code, we checked all cells in the matrix. However, this is unnecessary, since only cells that contain ones and cells that have at least one live neighbor can change state. It therefore makes no sense to check if we should, for example, update these cells, since none of these dead cells have a live neighbor. We could speed up the simulation by saving the positions or the ones in an array, and then just update these cells and their neighbors instead of all cells in the matrix. Another alternative to speed up the simulation in R is to create 8 new matrices that are shifted according to the Moore neighborhood. For example, this matrix has been shifted so that it corresponds to the northwest neighbors for all cells in the MAT matrix. To create a matrix that is shifted so that the pattern appears to be moving to the north, we change the order of the rows so that the first row becomes the last row of the shifted matrix. We create 8 new matrices that correspond to the 8 possible shifts. For example, we can see that the following cell has 3 live neighbors. If you sum the states of the corresponding element of the shifted matrices, we see that the number of live cells is equal to 3. Similarly, we can see that the following cell has 3 live neighbors, which correspond to the number of live neighbors in the corresponding cells of the shifted matrices. We can now compute the number of live neighbors for all cells in the matrix by simply summing the 8 shifted matrices. To implement the code using shifted matrices, we use the same first 6 lines of code as before. Next, we create the 8 shifted matrices. Then we define a for loop to update our matrices. Next, we sum the number of live neighbors by using the shifted matrices. Note that this is now done for all cells in the matrix at the same time. We next implement the rules. The conditions are checked for all cells in the matrix at the same time. Note that we now use the short version of AND, because we now like to evaluate all cells in the matrix at the same time. For example, if the cell is a live cell with less than 2 live neighbors, the following condition will be true for all those elements in the matrix. The elements that are true for the condition will therefore be set to 0 in the corresponding elements of the temporary matrix. Next, we update the states of the current matrix and the shifted matrices. Finally, we simply plot the matrix with an image and a grid. Note that we now only need one for loop this time, which will speed up the runtime a lot, since R is working much slower using for loops. Note that, since we now use shifted matrices, we'll automatically generate periodic boundaries. So finally, I just wanted to show you where you can find the R code for this example. So you go to my home page here, and you click there, and it should be as easy as this. You just copy the code, and you open a new script in R, and you should be able to run. This was the end of this lecture. Thanks for watching and good luck with exploring the world of cellular automata.